G'day everyone. Today's Chem Help video is on electrochemical cells. These are relatively simplistic questions, but they're an application of redox chemistry that can often be a bit difficult for some people if you don't follow a set structure. If you follow a set structure, you can easily maximise your marks and find them a little bit easier, I hope. So let's have a look at some of the basics. First of all, electrochemical cells are an application of spontaneous redox chemistry. Now, if we go back to that particular concept, what we might have is we have something like this. We have a reactive metal, such as zinc, placed into the solution of ions of a less reactive metal, so for example, copper. Now, if we place zinc into copper, what we're going to get is we're going to get spontaneous redox chemistry. The copper is able to attract the electrons from the zinc. The copper is more likely to reduce, and the zinc, as a result of that, is oxidized. So what we get is we get the zinc turning into zinc ions, copper ions turning to copper metal, and we get a metal displacement reaction. Now, if we look at the E0 values for those two things, zinc 0.76 volts and copper 0.34 volts. Overall, positive E0, 1.10 volts, and we get our overall reaction. Now, what happens is over time, the zinc and copper will essentially swap places. That's a displacement reaction. The copper will be plated initially onto the zinc will dissolve into solution. The blue colour, which was due to copper ions, will turn into copper metal, that's salmon pink. Even though in reality it won't be a shiny salmon pink, it'll be more like a reddish deposit. So you've got to be careful with the data sheet there. And the zinc will turn from a silver metallic substance into a clear colourless solution. So we have metal displacement. Now the thing here, we have electrons moving. The electrons are being given by the zinc and they're being accepted by the copper ions. But we can't harness them because it's happening at the ion atom exchange level. All right, with an electrochemical cell, what we do is we separate the sites of oxidation from the site of reduction. By separating them out, we make the electrons travel through an external path. We can harness them then, and that's the basis of an electrochemical cell. So here's the structure for every electrochemical cell that we're basically going to work with. So we have two cells, or half cells, which essentially are beakers. We have two electrodes, we have a connecting wire, and we have some kind of load, or a voltmeter or a globe would be fine, but a voltmeter is good because we can measure the potential, which is the voltage. And also we have this thing here, which is our salt bridge. We'll come back to why the salt bridge is important in a minute. Okay, so what we do is we label the two electrodes. One will be called the anode and one will be called the cathode. I'll talk about that in a minute. We show what's in the solutions. Now there'll be another ion, of course. You can't just have a zinc ion solution. It has to be zinc nitrate or zinc sulfate or something like that, or copper sulfate, copper nitrate. In this particular example, we're ignoring those ions because they're spectators. We label the anode or cathode. All right, so in an electrochemical cell, the anode is the site of oxidation. Cathode is the site of reduction. It's always the same. Anode, oxidation, reduction, cathode. Now, an electrochemical cell, not an electrolytic cell, that's different, but an electrochemical cell, the anode is the negative because that's where the electron starts its journey through the cell. We start at the anode. Electrons move through the wire to the cathode and they are given the positive sign. The sign convention in electrochemical cells is anode's negative, cathode's positive. What else we've got? The salt bridge. All right, now the salt bridge is really important. What happens in this particular half cell, the anode, is the zinc turns into zinc ion. So it's creating positive ions. In this cell, positive ions are turning into the metal. That's what's going to happen in reduction. In both cells, what would happen is we get what's called polarization. So more positives being created here, positives being consumed, which would leave the negatives alone, creating a negative balance, and would cause positive negative imbalance. And that means that you create positives, the electrons won't flow anymore because they can't flow away from a positive charge, and they won't be attracted to a negative charge either. So what happens is the salt bridge evens that out, stops polarization. If we take the salt bridge out of the system, the electrochemical cell stops immediately and it won't work anymore. Now this can be something as simple as a soaked piece of filter paper in a salt solution. In this case, potassium nitrate. Sodium nitrate or potassium nitrate are our two go-to substances for salt bridge solutions because the potassium and the sodium and the nitrate don't interfere with reactions. Sodium ions and potassium ions are highly unlikely that they're going to be reduced. Nitrate ions don't appear on the SRP table, doesn't form precipitates, as you know, all nitrates are soluble. So those are really good choices. Sodium or potassium nitrate for the salt bridge stops polarization. What we show is we show how the zinc is oxidized in this particular half cell. So we write the half equation underneath with its voltage, and in this one we show the motion of the copper ions turning into copper metal. We show the half equation for the reduction, and we write the E0 value. Now remember, with this one, when we flip the E0 value from the SRP table, we change the sign. On the table it would be negative 0.76, but the reaction would be written this way. We write an overall reaction voltage by putting the two together, simply adding the anode and the cathode half cells. We also label the motion of ions in the salt bridge. Now, this is the easiest way to remember this. Cations go to cathode, anions go to anode. Even though intuitively we go, oh, plus and plus, well that shouldn't happen, plus and plus shouldn't attract. It's cations to cathode. The cations will even out the negative charge created by the consumption of this positive ion. The negative ions will move to the anode half cell and even out the zinc ions being produced here in terms of charge. All right. We show electron flow. Electrons always go anode to cathode, so we show them with electrons and an arrow. And what else have we got? We've got, essentially that's right, we've got all the different pieces of our cell labelled, so we get full marks for that. All right, so here's the procedure to draw an electrochemical cell diagram. First of all, draw the diagram. Use your ruler, make them big, because you've got lots of stuff to jot all around there, so make them big, use a ruler. Use the bottom of your ruler. It makes a really good beaker, by the way, so there's a tip. List all the possible oxidation and reduction reactions using the electrolytes and the electrolytes. I'll show you that in a minute. Pick the most positive reduction. That's going to be the cathode reaction. Pick the most positive oxidation. That's going to be the anode reaction. Add the anode and cathode reaction together to get the overall equation and calculate the E0 for the particular cell, and determine the flow of electrons, always anode to cathode, and finally determine the flow of electrons in the salt bridge. And that will complete the diagram. So let's do a couple. Alright, so here's an example. Here's my basic electrochemical cell diagram. There's very little change that we can encounter with these. Occasionally we might get a gas half cell, but that's something you can have a look at later. But this simply shows two beakers, salt bridge, two electrodes, and a conducting path, and a load. Okay, so this one is a lead and silver combination. What will happen when you put these two half cells together? What's the voltage? Will it be spontaneous or not? Now, it's always the metal into the solution of its ions. Now, you can have examples where you don't have a metal. You can have a carbon electrode or a platinum electrode, and you can have like permanganate turning into manganese, so you can do that. But these simplistic ones, we're simply looking at metal in its ions. Metal in its ions. So, which way will the electrons flow? How much voltage will I get out of this cell? And what will happen? Okay, so let's think. Lead, lead ions, silver, silver ions. So what we do is we find from our chart all the different reactions involving those four things. So lead going to lead ions going to lead, silver going to silver ions, and silver ions going to silver. So they're from the chart. All the reactions involving those four things from our SRP table. So we've got two reductions in this case, and so two reductions and two oxidations. Of the reductions, what's the most positive one? So there's a reduction, that's the most positive. And of our oxidations, we have that one, and we have that one, and that's the most positive. So these are our two. We just cancel those out. We don't need them anymore. Always the strongest oxidizing agent and the strongest reducing agent. So what was oxidized is our anode, negative. What was reduced? Cathode, positive. Salt bridge, always labeled salt bridge. Remember, potassium nitrate, sodium nitrate, they're your go-to substances. Now, write what's happening in the anode. Oxidation. Lead is going to lead ions. Show that with an arrow. Half equation, E0 value. Over there, silver is going to silver ions. Half equation, E0 value. Add the two E0 values together. We had to flip this one around from the chart. That's positive 0.13 plus positive 0.8, positive 0.93 volts. Definitely spontaneous, and that's how much voltage we get. And think about a standard electrochemical cell like a battery, what we would call a battery. They're about 1.5 volts, so that's not too far off that. Show the movement of ions. Remember, cations to cathode, anions to anodes. This is to stop polarization of our half cell. Show our electron movement, always anode to cathode. Now be careful of examples where they flip the anode to cathode and the electrons flow the other way. Make sure you don't always just show them going left to right. Show them going from anode to cathode. Overall reaction, balanced of course for electrons because there's only one electron from silver and 2 electrons from lead. And we've got everything we need for what's happening. So what would happen in this particular example is the lead would lose mass because it's oxidized. The silver would gain mass as it's reduced. Silver ions and silver metal, colourless silver metallic substance, some of the grey metallic substance, colourless ions. So we wouldn't see any colour change, but we would certainly see loss or gain of mass in this particular cell. So that's that one. Let's have another look at another one. See, same structure, no difference. Draw it up nice and neat. Okay, so this is an example where we've got non-metallic electrodes. Now, platinum is a good non-metallic electrode, but it's very expensive, of course. Carbon in the form of graphite works just as well. All right, so graphite electrodes. We've got iron, 2 ions in an iron sulfate solution, and we've got potassium permanganate solution. Different salt bridge this time, sodium nitrate, but still, that's totally acceptable. Let's write down the equations. Now, carbon doesn't appear on the SRP chart. Graphite is a non-reactive conductor, so let's have a look at that. All right, so iron 2. Now, there is no iron 3 in this cell yet. It will be later, but not at the moment. So you can't write an iron 3 half equation, although that's there, that's a product. All right, iron 2, 2 different ones. Potassium, sulfate. Now, sulfate doesn't appear on the SRP table, so you don't have to worry about that. And permanganate, all right, 1.51 volts. Pick the most positive oxidation and the most positive reduction. So in this case, we've got oxidation, reduction, so 3 reductions, 1 oxidation. So it's easy to choose what's the oxidation, there's only one of them. And the reduction is going to be the potassium permanganate. Okay, so now what do? We cross out the ones we don't need. So we don't need those ones. We label the cathode is where the reduction occurs. So this is a reduction half equation. Label the cathode positive, label the anode negative. Okay? Now we show what's going to happen in this half cell. We've got iron 2 ions, which are pale green, going to the electrode, losing an electron and coming off as iron 3, which are a pale orangey yellow colour. All right, so that's what's happening in that cell. In this cell, we've got permanganate ions going to the electrode, picking up an electrode in a reduction reaction and turning into, from dark purple to a very, very pale pink manganese ion. Half equations under each electrode, so iron going to iron 3, there's your value. Now it's negative, all right, be careful with that. But this is quite strongly positive. Permanganate turning into manganese ions, 1.51, put them together, 0.74 volts. That's the electrical potential of this particular cell. Show our movement of ions and salt bridge, positive to cathode, negative, anions to anode. It helps if you remember cations to cathode, anions to anodes, and an overall reaction. Now, you could write a really nice observation for this one. As the reaction progressed, the green colour turned yellow-brown as the iron 2 was turned into iron 3, and the dark purple permanganate faded to a very, very pale pink as the reduction reaction progressed. What would stop this reaction? When the ions are completely consumed in terms of iron 2 and the permanganate, or the salt bridge gets contaminated, or it dries out, or if I take the salt bridge out, or I cut the wire. All those things will stop this reaction. But if you want full marks on one of these questions, then these are the basic components that you need. And if you follow that system, going through the list, it's actually really easily. So hopefully that's helped you out. Now, so this video, I'm going to dedicate this one to some of my students. So to Porty, Anika, Lauren, Megan, Ali, and Chris. This one's for you. If this was helpful for you, can you please subscribe and click like, and hopefully we'll see you next time. Thanks very much.